Hi, let's talk about powers of the imaginary unit, or the imaginary number I. So you've been introduced to this in some videos or maybe some Algebra 2 lessons in the past, but we want to look at this again. Now the thing about I is you really can't reduce it any further down than just I or I to the first. So when we look at powers of I, there are things going on here with radicals and negatives and square roots, and sometimes we can break it down further. So our goal is to either get powers of I down to just I, negative I, or some real number that we can pull out of that. So I want to show you what's going on here. I know in some of the videos you've seen there are patterns like this explored. So hopefully by me going through it here, it's more apparent, and we'll expand on this. So the question we're ultimately going to get to is, which of the following is equivalent to I to the 41st? Oof. I don't think I've ever raised anything to the 41st, let alone an imaginary number. So let's give this a shot. First, let's look at the pattern. So I squared, if I is radical negative 1, squaring that, think about what happens here. Okay, squaring a radical usually just strips it down and leaves you with the interior number. That's no different in this number system. So the square of a square root is just going to leave you that core value of negative 1. So I squared, that's kind of easy to stomach there, is just negative 1. I to the third. Now think about I to the third. You could call it I times I times I, because that's technically, you know, I to the first, I to the first, I to the first. That adds up to I cubed. But you could also call it I squared times I to the first. So because of the exponent properties, we can add up to 3 a couple different ways. In fact, you could go I to the first times I to the second if you wanted. So I say all that to say this. If you know that this can be built out of I squared, which is just negative 1, and then I to the first is just I, then I cubed can be whittled down to just negative 1 times I, which is negative I. So that is better than writing I cubed, because you're just dealing with the imaginary unit at a more basic level with a negative coefficient. So I to the fourth, you know, you could go I times I times I times I, or you could say, how about this? I squared was kind of a nice result. What if we went I squared times I squared? You know, the exponent rules would allow us to add those exponents up because we're multiplying the similar base. So I squared times I squared, you substitute negative 1 in for I squared, and you get negative 1 times negative 1. So I to the fourth is just positive 1, a real number. All right, so some things happen now. When we keep going up with this, so I to the fifth, you know, well, I could go, you know, I times I times I times I, you know, 5 times, but you could do I to the fourth was a really nice result. What if I added up to 5 by going I to the fourth times I to the first? You know, we're really using that exponent property of, if I am multiplying bases, I'm adding exponents, okay? So 5 by way of 4 plus 1 means I can substitute, 1. I to the fourth was just 1 times, I. So I to the fifth is just I. Interesting. Well, what if we go on to I to the sixth? It may not be apparent to everybody yet, but again, lots of ways to add up to 6. 2 plus 4, 3 times 3, or 3 plus 3, I mean. I really like using 4 because it just turns out to be 1. So why don't we say 6 is equivalent to, you know, I to the 6 is equivalent to I to the fourth times I to the second. Okay, so that I to the fourth we know is going to just turn into 1. Okay, and I to the second, hey, that was also a nice result as well. It was just negative 1. So we end up with two values, 1 times negative 1, which simplifies just to negative 1. And we start to notice we are going through the same values that we did up here. We started with I, then we went to negative 1. And, you know, I could humor you and do I to the seventh, see if this, if our inductive reasoning here pays off. And I'm going to build 7 by way of 4 and 3. And sure enough, because I can base it out of 4 and say, okay, I to the 4th was just 1. And I to the 3rd, we know that that's negative I. Okay, oops. Negative, that's an I. You're going to end up with negative I overall. 1 times negative I is negative I. So we start cycling through this pattern that is found with the first 4 powers of I. And I know that may have been pointed out before, but here's a quicker way to reduce, any power of I. Okay? Because it rotates through these 4 values over and over and over again, what you want to do is take whatever that power is on I, okay? Take that and divide it by 4. Okay? Again, we have 4 possible different outcomes to powers of I, integral powers of I. All right, so you're going to get a number, all right? You're going to get a number, and you're probably going to get a remainder most of the time. That remainder is what you want to look at, okay? That remainder tells you what the answer is going to be. Let me show you. Okay, we again have 4 unique answers. It's either I to the 1st, I to the 2nd, I to the 3rd, or I to the 4th. And again, from our work here in the middle, I'm just going to summarize this down real quick. So I to the 1st is just I to the 2nd was negative 1, I to the 3rd was negative I to the 4th was positive 1. So let me do an example with you that's even crazier than our problem over here. Okay, what if we picked 57? So I to the 57th. Wow, I think I'm overdoing it with this. Going a little too fast. I got to clean this up. All right, I to the 57th. And I'm going to use red. We're getting kind of lost in the blue down here. All right, I to the 57th. My advice to you is take that integer power and go over to the side with your scratch paper and say, what is 57 divided by 4? Now, you already know it's way bigger than 4. You're going to cycle through this pattern up to 4 so many times. And we don't care how many times we go through that cycle. It's just going to repeat those 4 answers. We want to know, what do you land on? It's kind of like spinning a wheel. You pass all those values every time the wheel goes around. So here's what happens. Let's do the division real quick. 4 goes into 5 one time. Okay, subtract, bring the 1, drop the 7 down. I'm going too fast again. Okay, 4 into 17, 4 times. Okay, that because it goes 16, we subtract that. 16, come on. And we get 1. So our remainder is 1. Okay. So what do I do with that? How does that narrow it down to which number in the pattern here? Well, the remainder is going to point to the power. So if the remainder is, wow, come on, pen. If the remainder is 1, your answer is I to the 1st, okay? If your remainder is 2, our answer would have, wow, my stylus, oh my goodness, is negative 1. If your remainder is 3, the answer reduces to negative I. And what happens if something's divisible by 4? What remainder do we get if it goes exactly in perfectly? Well, when you're dividing by 4 and you get a 0 remainder, that means you landed right on the good grief, right on the multiple of 4. So if you get a remainder of 0, that means you have exactly a multiple of I to the 4th, which is going to reduce to precisely 1. So here, in my little canned example of 57, we got a remainder of 1, so the answer there is just I to the 1st, or just I. Now, we could do the same work. I know I'm taking a little bit longer here, but we could do the same work with this question. Okay, 41. In fact, you could do this division in your head. 41 divided by 4, that's going to go through the pattern of 4 outcomes 10 times remainder 1. And you just have to remember that remainder 1 is the power, okay, on I. So I to the 1 is just I. Okay? So my answer here would be B. I to the 41 is precisely I. Alrighty? Thanks for the question.